All right, welcome back. We've been investigating how to test hypotheses about multiple regression models. We started by first looking at how to test the significance of the overall model. We then looked at how to test the significance of individual slope coefficients, and in particular, how to test the null hypothesis that an individual slope coefficient is equal to 0. We used the extra sum of squares method to carry out these tests. But the extra sum of squares method can be used to test much more interesting and complex hypotheses than these rather simple ones. And that is what we'll be looking at in this lecture video. Now again, we'll be using SAS to perform these analyses. In particular, we'll be using both PROC-IML, the interactive matrix language, as well as PROC-Reg to implement these tests using the extra sum of squares method. Finally, we'll see how to perform hypothesis tests using the test statement in PROC-Reg. Using the test statement in PROC-Reg frees us from having to validate PROC-IML programs or copy values from SAS output into subsequent data steps. We can instead focus on specifying the hypotheses of interest to the test statement and have assurance that the test will be carried out correctly. So let's check it out. Okay, this video is based loosely on examples 3.6 and 3.7 in the text. I say loosely because in those examples, they don't actually analyze a real data set. And so what I've done for the purposes of this video is create a simulated data set so that we can actually have some data to analyze. Now, in this example, we're going to be working with the multiple regression model given here, y equal to beta 0 plus beta 1 times x1 plus beta 2 times x2 plus beta 3 times x3 plus the error term. So this is a multiple regression model with 3 explanatory variables. Now, there are 3 hypothesis tests that we'll be looking at. The first hypothesis test is very similar to the one we looked at in a previous lecture video because it involves a single slope coefficient, beta 1. But in this case, instead of testing the null hypothesis that beta 1 is equal to 0, we're going to test the hypothesis that beta 1 is equal to 1 against the alternative that it's not equal to 1. So that's a little bit more general than the hypothesis that we looked at in a previous lecture video. Then the second hypothesis test we'll look at is the null hypothesis that beta 2 and beta 3 are equal to 0. They're equal. All right, we're not specifying what they're equal to, but they're equal to each other. Now, that's equivalent to saying that beta 2 minus beta 3 is equal to 0, right? And so that is the null hypothesis that we'll be testing. So this is certainly a much more complex hypothesis test than we looked at in our previous lecture video. And then finally, in hypothesis 3, we're going to be combining these 2 null hypotheses into a single null hypothesis. The null hypothesis will be that beta 1 is equal to 1 and beta 2 and beta 3 are equal against the alternative hypothesis that either beta 1 is not equal to 1 or beta 2 is not equal to beta 3. Now, to perform each of these hypothesis tests, we're going to use the extra sum of squares principle. All right, and in this first program, we're going to be using PROC-IML to carry out the analysis. So let's check it. Let's check it out and see how we do this. So let me scroll down here. And the first thing we have to do is we have to bring in our data set. And so what I've done here, I've got the data set is stored as a SAS data set, and it's in a particular directory on my computer. And so in order to point SAS to that particular folder, I have to create a libref, and that is done with the lib name statement. And so the libref is actually SAS underscore data, right? That's a pointer to this particular folder or directory on my computer. And when you download the data set, you'll just have to change the lib name statement so that it points to the directory in which you saved the SAS data set. Now, the SAS data set, the file name is called ex06, so example 6 underscore data. All right. And notice that when I open this data set, I have to specify or tell SAS that it's in the libref pointed to by SAS_data. And so I first create a libref using the libname statement. All right, and then I use that libref in my data step. And so what I'm doing here is creating a temporary data set, calling it EX06. And then I read in the data from the actual data set. And then remember that in proc IML, I need the first column of that design matrix X to contain ones. Those ones are not contained in the SAS data set. And so what I'm going to do is just do a statement here, X0 equal to 1. All right, and what that's going to do is it's going to create a variable in the SAS data set that contains the value 1 for every observation. And so it's just easier that way to do it here in the data step than it is to do that in proc IML. Now, you'll recall that in the previous lecture videos, we created the necessary vector and matrices by entering the data into matrix literals. But in this particular program, in this video, I'm going to show you how to read in an existing SAS data set. So we've created this temporary SAS data set, EX06. And what I'm going to do in proc IML is I'm going to tell proc IML to use that data set. So essentially what that does is it tells proc IML to open up that data set and make it available to proc IML. Then what I need to do is I need to read in various variables into vectors and or matrices in proc IML. And so the way to do that is to use the read statement. And so this first read statement tells SAS, tells IML to read in the values, all values in the data set or all observations in the data set for variable y, and store those values or put them into a vector also called y. So it differentiates between the vector y and the variable y by virtue of the fact that the variable y is contained in the curly brackets here. Then what I need to do is I need to read in the values of x0, x1, x2, and x3 from the SAS data set into my design matrix X. And I do that again using the read statement. Read all from the variables x0, x1, x2, and x3 into a matrix of appropriate size having 4 columns and a number of rows equal to the number of observations in the data set. And then what I'll do so that we can see to make sure that we've imported those values correctly, we'll just print those out. Okay, now let's scroll down a little bit. The first part of this proc IML program is the same as you've seen in previous lecture videos. And so I am analyzing, I'm constructing the full model, analyzing the full model, building or fitting the full model. And so to do that, I have to estimate the model parameters, and that requires calculating the X prime X matrix, the inverse of the X prime X matrix, the X prime Y vector, and so forth. All right. And so let me scroll down a little bit further to get by all this because we've already seen all this. I'm not going to dwell on it. The section I want to see is starting down here. So once we get to this point, okay, this is where we're finishing up the analysis. All right, we're printing out the value of the F statistic, the p-value. We're calculating and printing out the coefficient of determination, which is r squared, and also the adjusted r squared. All right, so we've seen everything up to that point. Okay, now we're going to test hypotheses using, for lack of a better term, the standard F-test approach. All right, or we could call it a t-test as well. We could perform a t-test. but I'm going to use the squared version of a t-test, which again, you'll recall is an f-test. Now you'll remember that a t-statistic is essentially the point estimator of the parameter you're testing hypotheses about minus the hypothesized value, and then you divide that difference by the estimated standard error of the point estimator. All right, and so that's what I'm calling kind of the standard t-test approach. And then if we square that, we get an equivalent f-test. So that's what I'm going to be implementing in this particular section of code. And so you can see here that what I'm doing in this first row here, and I've got the numbering turned on, so row 153. All right, so I'm going to call this test statistic f. And the numerator, you can see it's a ratio. The numerator is the square of the difference between the point estimator of, in this case, beta 1. All right, so again, yeah, these are the hypotheses we're testing, that beta 1 is equal to 1 against the alternative that it's not equal to 1. So the parameter of estimates is b hat, b underscore hat, and the second entry in that vector is the point estimate for beta 1. And so the numerator of this f statistic is the square of what we'll call beta 1 hat minus its hypothesized value, which is 1. All right, so we square that difference, and then we divide that difference by the variance of beta 1 hat. Now, what I've done here, here I have what I'm calling b hat underscore cove. All right, and so let me just scroll back up here, and let me see if I could find that. Okay, so right here is a little bit of code that I added in addition to the previous code that I had. So this might be a little bit different than what you have in one of the other programs that you've downloaded, but I'll upload this program to Moodle so that you can have this. But what I'm doing here is I'm constructing the estimated covariance matrix of the vector of parameter estimates. All right, and I'm going to call it b underscore hat underscore cove. And that estimator is equal to the product. We're multiplying a scalar, the MSE. Remember, the MSE from the full model is our estimator of sigma squared, the variance of the error term. We're multiplying that scalar against the matrix x prime x inverse. And that gives us the estimated covariance matrix of b hat. Okay, so let's scroll back down here. Okay, and so, yeah, right here. Okay, so the numerator, again, of the f statistic is the square of the difference between the point estimator of beta 1, which is beta 1 hat, minus 1, the hypothesized value. And then we divide that squared difference by the variance of beta 1 hat. And that variance is contained in the 2 entry in this covariance, the estimated covariance matrix. So that's all I need to calculate the test statistic. I'm going to give it a little bit different format than what it had above because I want to see several decimal places. We'll print that out. And then we will calculate the p-value for the test. All right, and so as arguments to the prob f function in SAS, I've got the value of the test statistic, which was f. And then for this test, because there's only one constraint, there is one numerator degree of freedom. And then for the denominator's degrees of freedom, that is equal to the number of error degrees of freedom from the full model. Okay, and so that is how we implement that test. Then let's take a look at how to perform hypothesis test 2. And so again, the null hypothesis is that beta 2 is equal to beta 3 against the alternative that beta 2 is not equal to beta 3. Now, this null hypothesis, as we said before, is equivalent to the statement that beta 2 minus beta 3 is equal to 0. And so that's helpful because in order to construct the F statistic, again, we have to have a point estimate of the statement that is in the null hypothesis, right? And so that's why we need to restate that as a difference. And so the point estimate of beta 2 minus beta 3 would be beta 2 hat minus beta 3 hat. And so beta 2 hat is in the third position in B underscore hat, and beta 3 hat is in the fourth position. From that difference, we subtract off the hypothesized value of the difference, which is 0, and then we square that difference. Next, we have to divide that squared difference by the variance of the estimator of beta 2 minus beta 3. The variance of beta 2 hat minus beta 3 hat, you may recall, is going to be, it's a little bit more complicated, all right, but it's essentially the variance of beta 2 hat plus the variance of beta 3 hat, and then because we have a minus sign here, minus 2 times the covariance of beta 2 hat and beta 3 hat. Right, and so that is the formula for the estimated variance of beta 2 hat minus beta 3 hat. And so again, that's the standard form of the F statistic for this kind of test. All right, so we'll print that out, take a look at it in the output, and then we will calculate the p-value. And again, because there is only one constraint in this null hypothesis, there's one numerator degrees of freedom for the test. For the denominator degrees of freedom, that's equal to the number of error degrees of freedom for the full model. Now, in addition to the what we're calling the standard F-test approach, we're going to use the approach that is shown on page 97 in your textbook. And in particular, the test statistic formula is given in equation 343. Now, this is a very nice approach. It's a very general approach. It's very easy. Once you get the code set up, it's very easy to test a wide variety of hypotheses using this particular setup. And so what I want to do is, before we look at the output, before we run this program and look at the output, I want to show you how we're going to implement this particular test. And we'll do this for all three tests, right? We'll do it for hypothesis test 1, hypothesis test 2, which we are doing up above using the standard F-test approach, but we'll also include hypothesis test 3 in this framework as well. So again, we're going to be looking at first hypothesis test 1, testing the null hypothesis that beta 1 is equal to 1. And so what we're going to do, and you'll need to spend some time looking at that formula in equation 3.43, but essentially the first thing we have to do is construct a hypothesis matrix. Now in the notes or in the text, they're using the matrix T to represent that hypothesis or that matrix of coefficients that implement or constrain the model based on the hypothesis. But here in IML, T is used, it's the transpose function. So I don't want to use the same letter because that might be confusing. And so what I will do is use the H to represent this kind of a matrix. Okay, and so what we're going to do is we're going to multiply the H matrix against the beta vector. Now the beta vector in this case is a 4x1 vector, 4 rows, 1 column. All right, this H matrix you'll see is a 1x4 vector, it's a row vector. And we want to pull off beta 1 out of that beta vector. And so the way we do that is we have a 1 in the second position, which corresponds to the row in which beta 2 shows up. In which beta 1 shows up in that beta vector. And then we have zeros everywhere else. All right. And then what we have to do is we have to have in this case, a 1-by-1 matrix in order to get PROC-IML to do this that corresponds to or contains the hypothesized value for beta 1. Now, again, in the textbook, they use the lowercase vector c, all right, but we are potentially using C for something else in these PROC-IML programs. And so I'm going to use D instead. Okay, so again, this vector H allows us to pull off beta 1 out of the parameter vector. And then the D is specifying the hypothesized value for that parameter. Now, R is the number of numerator degrees of freedom. That's given by the number of rows in H. And then once we have all that set up, then this is the form of the test statistic. So it's again, well, I'm going to call it F because it is an F statistic. In other words, we're going to go to the F table, the F distribution, as the reference distribution for looking up critical points or calculating p-values. And so you'll see here that what we have here, we have the transpose of H times beta hat. Remember, H is right here. So the transpose of H times B hat minus D times the inverse of this matrix. And so we have H times X prime X inverse times the transpose of H. So we have to take the inverse of that matrix product. And then we post multiply that by H times B underscore hat minus D. And then once we have that, we divide that by R. All right, and they do use lowercase r in the formula in the textbook. So that gives us the numerator for the F statistic. The denominator is the MSE from the full model. So that is the estimator of the error term based on that full model. So that is how we calculate the test statistic using equation 3.3. Okay, and then we'll print that off so we can check it out. We'll also calculate the p-value. And notice here that, again, we've got the F statistic as the first argument to the prob F function. Then we specify the numerator degrees of freedom and the denominator degrees of freedom. Okay, now let's look and see how to use this technique to perform hypothesis test 2, which again is the null hypothesis that beta 2 is equal to beta 3, or in other words, beta 2 minus beta 3 is equal to 0, against the alternative that the difference is not 0. Okay. All right. So again, what we need to do is set up the appropriate H matrix. And because we want the difference between beta 2 and beta 3, the appropriate H matrix would have zeros for the first 2 columns and then 1 to pick off the beta 2 and a -1 to subtract beta 3 from that. And then the hypothesized value is 0. And so our, in this case, 1-by-1 matrix D has the values 0 in that. Now, once we have specified the H matrix and the D matrix, all right, then the F statistic is computed in exactly the same way as it was up here. And if you look at that, you'll see that those are exactly the same. All right, so the only difference is the information or values contained in the H matrix and the D matrix. All right, and then let's look and see how to implement hypothesis test 3. So in this case, in this null hypothesis, we have not only beta 1 being equal to 1, but we have also beta 2 being equal to beta 3. All right. And so because we have 2 constraints in this null hypothesis, we're going to have 2 rows in the H matrix. And so that's reflected here, again, by the fact that we have that comma. All right. Whenever you have a comma, it means what comes next goes on the next row in the matrix. And so in the first row, we're wanting to specify the coefficients that will allow us to specify this constraint, beta 1 equal to something. And so we have a 0, 1, 0, 0. So that picks off just beta 1. And then in the second row, we want to specify coefficients that will allow us to pick off a positive beta 2 and then a minus beta 3. And so the coefficients would be 0, 0, 1, negative 1. And so essentially, the first row is the row that we had in the H matrix for the first test. The second row is the values we had for the second test. We're just combining those two, and it has to be in different rows. Now, again, in this case, because we have two constraints in the null hypothesis, our D matrix is not 1 by 1. It's got two rows, one column, so it's 2 by 1. So in order to specify that beta 1 is equal to 1, that first entry has to be 1. And then to specify that the difference between beta 2 and beta 3 is equal to 0, we have a 0 there. So again, in order to test this hypothesis, it requires constructing the appropriate H matrix, the hypothesis matrix, and the D matrix. Once we have those, though, the formula for the test statistic is exactly the same as it was for the other, at least in terms of the matrix representation, right? From that abstract viewpoint, it's the same thing. And so we don't have to modify this the formula for this test statistic. Okay, then we'll print that out so we can take a look at it and calculate the p-value. All right. So let's go ahead and run this, and let's take a look at the results. Okay, so let's go to the very top. Okay, so here I'm printing out the data. I've got the y values, the vector of y values, and then I have the design matrix containing the first column of ones, and then the subsequent columns for x1, x2, and x3. And we don't have observation numbers here, but there are 100 observations in this data set. All right, that's reflected by this first entry in the x prime x matrix. Shows the sample size. All right, and then we're not going to look really too much at this output. This is output that we've seen, this type of output in the past, although we could look at the parameter estimates. So the intercept looks to be about 8. Beta 1 hat is a 0.8589. And then beta 2 is a 1.0866. And beta 3 hat is 1.2900. All right. And so we see here also values for the Anova table for this regression. The sum of squares error is 5137.3664. We've got 99 total degrees of freedom. The regression model has 3 degrees of freedom associated with it, and there are 96 degrees of freedom for error. The mean squared for the regression is 261.46037, and the mean squared error is 53.514233. Now also notice here B hat cov. This is the estimated covariance matrix for the parameter estimate vector beta hat. And so we have the variances of the estimates down the diagonal. All right, so 127.7, 0.242, 0.2604, and then 0.2258. Those are the estimated variances of beta 0 hat, beta 1 hat, beta 2 hat, and beta 3 hat, respectively. And then the off-diagonal elements would be the estimated covariances between pairs of those estimated or pairs of those estimators. Okay, now let's, and by the way, we see here that the F statistic for the significance of the overall model is 4.89, and the p-value is 0.00333 approximately. And so we see that at least one of these slope coefficients is, we would conclude that at least one of the slope coefficients is non-zero. The R squared value is 0.1325. The adjusted R squared value is 0.1052. So the model does not fit the data very well, but it is statistically significant. Okay, now let's look at the results of these tests. So the first thing we're doing is testing the null hypothesis that beta 1 is equal to 1. Now let's just suppose that this is a situation where the researcher had reason to believe that the slope coefficient on x1 would be 1. All right, and now this is a simulated data set, okay, and you wouldn't want to base this hypothesis based on looking at the data. You would want this kind of hypothesis to be generated or flow from the theory of the field from which the data comes from. All right, so let's just assume here that there's something about the process that generated the data that the researcher leads the researcher to believe that beta 1 may be equal to 1. So we're going to test that hypothesis. Okay, so you saw how we constructed that test statistic. If I go back in here, all right, this is the section of code that is generating the output. And we see here that the F statistic is 0.0821. So very small, very close to 0 actually. And the p-value is therefore 0.7751 approximately. So there's insufficient evidence at any reasonable significance level to conclude that beta 1 is different than 1. All right, so we fail to reject that null hypothesis that beta 1 is equal to 1. Okay, next, let's look at hypothesis 2. Again, we're testing the null hypothesis that beta 2 and beta 3 are equal. And so again, let's just pretend or assume that this is in this particular context, the researcher has reason to believe, or at least it's an interesting theoretical question to see whether beta 2 and beta 3 are different. And so the assumption going into that would be that they're the same, and then we'll let the data try to convince us otherwise. In other words, is there sufficient evidence to conclude that beta 2 and beta 3 are different? Well, in this situation, again, the F statistic is very small, 0.8137 or 0.081375. The p-value for that is 0.7761, really the same as this other value. And right here, very close to it at least. And so we see here that there is insufficient evidence to conclude that beta 2 and beta 3, the slope coefficients on x2 and x3 are different. Okay, now, the next thing we're going to do is we're going to look at this procedure for implementing the extra sum of squares method using the equation using equation 3.43 in the textbook. Okay, and so that is what we're doing here. And we're again testing this null hypothesis that beta 1 is equal to 1 using that matrix approach. And so I printed out here my hypothesis matrix as well as my D matrix. And then let me go back here to the code. All right, so we print those out and then we calculate the F statistic, print out the F statistic, and then print out the p-value. That's what's visible from the output. And so you see here that the F statistic is 0.082128. Well, let's go compare that to what we got with the other method, the standard method, 0.082128. 0.082128. So we get the same exact thing. The p-value that we got using the standard method was 0.77505. Using equation 3.3 approach, 0.77505. So this is exactly the same test. It's just implemented, in a different way using these matrices. All right, and so you see you get the same exact value. Okay, next let's look at testing hypothesis 2. So testing the null hypothesis that beta 2 is equal to beta 3 against the alternative that they're different. Again, this is the appropriate H matrix, hypothesis matrix, to generate that test. The D matrix is 0. The F statistic, calculated using equation 3.43, is 0.081375. And that is exactly what we got using the standard F-test approach, 0.081375. The p-values are therefore the same as well, 0.776057. And so you see here that we can perform these tests using either the standard F-test approach or this approach that uses equation 3.43, and we get the same exact results. Finally, let's look and see how to test the null hypothesis with this certainly much more complex null hypothesis, that beta 1 is equal to 1 and beta 2 is equal to beta 3. And so to do this, again, we have, in this case, a hypothesis matrix that has 2 rows. The D matrix, therefore, has 2 rows as well. The F statistic for this test is 0.078430, and the p-value is 0.9246. So there's no evidence at all that this null hypothesis is false, right? So there's insufficient evidence at any reasonable significance level to reject the assumption that beta 1 is equal to 1 and beta 2 and beta 3 are equal. So that is how we can test these hypotheses, and some of these are fairly complicated, fairly complex. We can do this using the extra sum of squares principle. Okay, and in particular, this is how we can implement that test in Proc IML. All right, so again, we can roll our own, so to speak, using the interactive matrix language in SAS. All right, next, let's see how to do these analyses using the extra sum of squares principle in Proc Reg. And so we have the same setup, the same situation. We're looking at using the same data set, fitting the same multiple regression model. We're testing the same 3 hypotheses. We're going to use Proc Reg to implement the extra sum of squares method. And this is how we did it in previous lecture videos. We didn't fit models that were as complex or hypotheses that were as complex. All right, but it's very easy to do. You're going to find that it's very easy to implement the extra sum of squares method using Proc Reg, or if you're using another program like R or SPSS or Minitab or something like that, all you have to do is fit a full model and a reduced model. And as long as you do that, then you can get the required quantities very easily for performing the extra sum of squares test. Now, in addition to using Proc Reg to implement, in some sense by hand, the extra sum of squares method, we're also going to see how to use the test statement in Proc Reg to perform these tests. And this is really, really nice. I guarantee you, you're going to like the test statement of Proc Reg, because it's going to allow us to implement these tests very, very easily. All we have to do is focus on specifying the information to the test statement correctly, and it will perform all of the calculations that we've been doing in Proc IML. It'll do that in the background. It'll do it right every time. Okay, so let's see how to do this. All right, so again, I need to open up a version of the data set. Okay, and then, and I'm not going to bother printing the data out or constructing scatter plots. You can do that. I'll leave this in the code, and you can do that when you run it on your own. All right, and so then what we need to do is we need to fit the full model, right? So in order to implement the extra sum of squares principle, we have to have a full model, and then we have to have one or more reduced models that correspond to the various hypotheses that we may want to test. All right, so let me go ahead and I'm going to run this code, what that'll do is it'll clear out the results viewer, and it will run the full model. Okay, and so that's the output that we have. Notice that what I'm doing here, when I run this full model, is I'm selecting just the Anova table for the regression. I want to keep, I don't want to see everything else because I want to keep the output kind of clean so that we can focus. All right, and so this is the Anova table for the full model. And so we'll need the error sum of squares. We'll need the mean squares for the full model. We'll need to see the degrees of freedom associated for error with the full model. We'll be using that as we implement this extra sum of squares method. Okay, now we're going to perform the hypothesis test using the extra sum of squares method by fitting the full and the reduced models. And so the first hypothesis test that we're going to perform, again, is the null hypothesis that beta 1 is equal to 1 against the alternative that beta 1 is not equal to 1. Now, in order to do this, in order to fit this restricted model, what we do is we write out the model and we replace beta 1 with its hypothesized value, which is 1. Now, the x's are known, and if beta 1 is in fact equal to 1, then that quantity is known. And so we can subtract that from both sides of the equation. And when we do that on the left-hand side, we get y minus x1. And on the right-hand side, we have what's left, beta 0 plus beta 2 times x2 plus beta 3 times x3 plus epsilon. Well, what we have here is a new response vector. Instead of y, we have y minus x1, and I'm going to call that y star. Okay, so we essentially are going to fit this regression model that has two explanatory variables against this new response variable y star. So that's how we implement the restriction in proc reg. And so what I'm going to do is I'm going to calculate or construct a new data set. I'm going to call it reduced. All right, so with this data step, I'm creating a temporary data set called reduced. I read in all the values from the original data set that we started with. And then I'm going to define a new variable called y underscore star, and that's equal to y minus x1. Then when I run proc reg, I'm going to use that data set, and I'm going to have y star as the response variable. And then I have x2 and x3 as the only explanatory variables in that model. And then again, I'm going to select just to output just the Anova table for the regression so that we can get the values we need. So let me go ahead and run this section of code. And so now here we have the Anova table for that reduced model. We'll need to get the sum of squares error for that model. We'll need the model error degrees of freedom. Okay, and so then what we do after that, and this is what we did in the previous lecture video, we're going to, instead of having to do complicated data steps to get the values from those Anova tables, we'll just copy and paste, all right? So that, for the sense of understandability, that's going to be sufficient, all right? And so let me see what we need here. We need the sum of squares error for the full model. We need the sum of squares error for the reduced model. All right, and so those values are given here and here. And so we just copy those into this data step. And this is the same data step, or it's very similar. It's not quite the same because now instead of expressing the difference in terms of the model sum of squares, I'm doing it in terms of the error sum of squares, which we need to do. Okay, so I've copied in the values for the sum of squares error for the full model, the sum of squares error for the reduced model, and then I take the difference, the sum of squares error for the reduced model minus the sum of squares error for the full model. Then we need to calculate the degrees of freedom for the test, and so we need the degrees of freedom for error for the full model and for the reduced model. Okay, and again, those are given Let me see here. Those were given here and there. All right, and then the degrees of freedom for the test would be the difference in the number of error degrees of freedom for the reduced model and the error degrees of freedom for the full model. We also need the mean squared error from the full model. That is our estimate of sigma squared, the variance of the error term. Okay, so I'm going to call that MSE underscore full. And then we calculate the test statistic. All right, and this is how we did it. It's equivalent to what we did using the standard F-test approach in the IML model. So it's the sum of squares underscored the difference divided by the degrees of freedom for the test divided by MSE full. Okay, and then the degrees of freedom for error. And let's see, I've got that. I guess I don't need that. I could just, let me do this instead. Right there, and I'll comment this out for now. I'll take it out before I upload that. Anyway, so that's going to allow us to calculate the F statistic, the p-value, and then we'll print those values out. So let's print this and see what we get. Okay, so we see here that the F statistic is 0.082128, and the p-value for this test is 0.77505. Now, we don't have those available anymore because we cleared out the viewer, but go back when you do this, either go back in the video and check this out. Maybe you wrote it down and can look at it right now and verify it, but those are the exact same values for the F statistic and the p-value that we got for this test using proc IML, both using the standard approach and the approach using formula or equation 3.43. Okay, now let's move on and let's test hypothesis 2. All right, and the null hypothesis for hypothesis 2 is that beta 2 is equal to beta 3. All right, and so if we implement that in our model, we have the model, the reduced model, being equal to y plus beta 0 plus beta 1 x1 plus beta 2 times x2 plus beta 2 times x3, because beta 2 and beta 3 are equal. So we have beta 2 here and beta 2 here, and then plus the error term. Now we can factor beta 2 out of that sum, and so this simplifies to beta 0 plus beta 1 times x1 plus beta 2 times the quantity x2 plus x3 plus the error term. And we can, let me make this a little bit more readable here. Okay, we'll put the multiplication sign there. And so that finally simplifies to beta 0 plus beta 1 times x1 plus beta 2 times x2 underscore star. We'll call it, call this new variable x2 underscore star, where that new variable is equal to the sum of x2 and x3. So in order to fit this reduced model, what we're going to do is create a new variable called x2 star, which is the sum of x2 and x3, and then just do a regression on that data set using that particular variable to fit this particular model here. And so you can see that that's what we've done. I've taken that reduced data set and I'm opening it back up, and I'm going to add a new variable called x2 star, which is the sum of x2 and x3. And then I use that data set in proc reg. And for my model statement, I have the original y vector, y, the original response, equal to x1, because we have x1 here, plus x2 star. And so that is how we fit this reduced model. So let's go ahead and run that. And notice again that I'm going to be outputting only the Anova table for the regression. Okay. Okay, so here is the output for showing the reduced model for testing hypothesis 2. And you see here that we have the error sum of squares of 5141.72113. We have error degrees of freedom 97. All right, and so now we go back and you can see here again in this section of code that we're just to make it easy, copying the values from the output. So 5141.72113. That's what we've copied into this place. We've got the correct number of degrees of freedom for the reduced model. And so if we run this, and I'll fix this later when before I upload it, let's go ahead and run that section. Okay, and so you see here that the F statistic is 0.081375, and the p-value is 0.77606, and that's exactly what we got when we ran or did this analysis in Proc IML. Okay, and then finally, let's perform hypothesis test 3. And so the null hypothesis here is beta 1 is equal to 1 and beta 2 is equal to beta 3. When we incorporate both of those constraints into the model, we get the new model, the reduced model, y star equal to beta 0 plus beta 2 times x2 underscore star. All right, and so then when we run the model, that is the model that we fit. So you can see here in the model statement, y star equal to x2 underscore star, because that's the only explanatory variable in the model. Okay, and so when we run that, we get this output. This is the Anova table for that regression. All right, and so for example, the sum of squares error for that model is 5145.76064. And that is what we've got here. And then we also have, for this model, we've got 98 error degrees of freedom. And so we need to be sure that we specify that. And you can see here that the number of degrees of freedom for this right here, that's for that's the denominator degrees of freedom. Okay, and that's still specified correctly, but I need to clean that up in the code. All right, and so then the degrees of freedom for the test is going to be the difference in the error degrees of freedom for the reduced model and the full model. So in this case, we're going to have 2 degrees of freedom for the numerator. Okay, and so then let's go ahead and run this. And so the F value, the F statistic, is 0.078430, and the p-value for this test is 0.92463. All right, and so again, those values are exactly what we got when we ran this, when we implemented this in Proc IML. So I think what you're seeing here, I'm sure you can appreciate this, is that in order to, well, number one, we can test really complex hypotheses using the extra sum of squares method. And it's very easy to implement this method because really all it requires is implementing 2 models, the full model and a reduced model that implements the constraints or imposes the constraints that are in that null hypothesis. And then once we get the values from those 2 fits, then we can put them together using this formula for the F statistic. So it's a very powerful and very easy way, relatively easy, to do these analyses. But I want to show you one more way to do it, and it's even easier. All right, and this is using the test statement in ProcReg. And I guarantee you, you're going to like this. So the first thing we'll do again is test hypothesis 1, the null hypothesis being that beta 1 is equal to 0 against the alternative that it's non-zero. And so what we're going to do is we're going to fit the full model. Right? We have all of our explanatory variables in the model. And notice that I'm using the original data set. I could use the reduced data set because I did not change these actual variables, but just to keep everything clean and make sure that everything is in good shape, I'm going to go back and use that original data set, and then I'm going to fit the full model. And then what I'm going to do is I'm going to issue the test statement. And as an argument to that test statement, I'm going to implement the constraint that is reflected in the null hypothesis. And so the null hypothesis is that beta 1 is equal to 1. And the way that you would specify that is you would tell the test statement that you would say x1 equal to 1. And now this does not mean that x1 is equal to 1. It means that the coefficient of x1 is equal to 1. That's how proc-reg interprets that. And that's all you got to do. You don't have to fit two models. You don't have to construct matrices and do complicated calculations. You don't have to use the prob-f function to get p-values and so forth. All you have to do is to specify the test statement. And so let's run this and see what happens. And so here we have the output. And again, notice that what I'm doing is I'm telling it to only print out the results that are in what's called the test Anova table. And so that would include, that's the values, the result from the test statement. So let's take a look. And so here we have an F statistic for this test. Notice that this is a 1 degree of freedom test. The F value rounded to 2 decimal places is 0.08. And the p-value to 4 decimal places is 0.7751. Now, let's go back and compare that to what we got using proc-reg, implementing the extra sum of squares principle. We got an F statistic of a p-value of 0.77505. Now, if we round that to 4 decimal places, we get 0.7751, exactly what we got from the test statement. Isn't that easy? All right, now let's perform hypothesis test 2. All right, here we're testing the null hypothesis that beta 2 and beta 3 are equal against the alternative that they're not equal. Well, the way to do that is to think of that null hypothesis as being written as a difference. And so beta 2 minus beta 3 is equal to 0. And that's what we have here in the test statement. But again, instead of beta 2 and beta 3, we have to use the variables because that's all that SAS knows about. Okay, so test and then x2 minus x3 equal to 0. And proc-reg interprets that as saying that beta 2, the coefficient on x2, minus the coefficient on x3 is equal to 0. And it's going to implement that restriction automatically and then perform the test. And so let's see what we get with that. And so for that test, the result is, again, an F value of approximately 0.08. The p-value is 0.7761. If we go back up here, in fact, we can have both of them on the screen at once. All right. So here are the results using proc-reg, all right, where we're fitting two models by hand, all right, and then doing those calculations in a data step. The p-value, well, number one, the F value, the F statistic is 0.081375. The p-value is 0.77606, rounded to 4 decimal places, 0.7761. So exactly the same value. And then finally, let's fit the most complex model that we've looked at today. Let's fit hypothesis 3, the null hypothesis being that beta 1 is equal to 1 and that beta 2 is equal to beta 3, or equivalently, as we know, beta 2 minus beta 3 is equal to 0. And all we have to do is to issue the test statement. And in the test statement, say x1 equal to 1, comma, x2 minus x3 equal to 0. All right, so we have those two constraints that are stated in the null hypothesis listed in the test statement separated by a comma. That comma's got to be there. And then that's all you've got to do. So let's run that and let's check out the results. We see here that the p-value for this test, 0.9246. You can see up here that when we did it by hand using proc-reg, fitting a full model and the corresponding reduced model, or the appropriate reduced model, doing those calculations, copying the appropriate values into the data step, running that data step to get the p-value, we got the same exact thing, 0.92463. So again, we've seen how to implement this extra sum of squares method in proc-IML, how to implement it in proc-reg by fitting by hand or intentionally fitting two separate models, the full model and a reduced model. And that works, but there is a bit of work to it, and we do need to make sure that the programs that we've written, and in particular the programs in IML, that they're validated and that they're producing what we want them to produce. But we can get the exact results we want using the test statement in proc-reg, and we don't have to validate, we don't really have to quality check anything except to make sure that the test statement is correct, that it actually implements the null hypothesis. And so we can focus our energies and our attention on the test statement, and just to make sure that we're accurately reflecting that null hypothesis. But once we've done that, we know that the procedure is going to run perfectly. It's going to give us accurate results. So that is how we can utilize the extra sum of squares principle to test much more interesting and much more complex hypothesis tests than merely testing whether or not a given slope coefficient is 0. We can actually test hypotheses about collections of slope coefficients all at once. We can test hypotheses that have constraints or relationships between the slope coefficients. And we can do this using a multitude of tools in SAS. And if you've got another language that has matrix capability, like MATLAB or something like that, or then you can implement these proc-IML routines there as well. All right, and really with any statistical software that does regression, you can use the extra sum of squares principle by hand by fitting separate models and then going through those small number of calculations to get the appropriate F statistic or get the F statistic and the p-value. But again, you really don't even need to do all that, because in proc-reg, we have the test statement, and that really, that's the workhorse that does all these kinds of tests for us. So I hope you like that. I think that you'll find it interesting, and I think that you'll get a lot of mileage out of that. And so we'll continue on in the next lecture video.